This video will explore CodeBERT, a new model for combining neural representations of natural language with programming languages by leveraging documentation of functions in languages like Python, JavaScript, and PHP. CodeBERT uses masked language modeling on the natural language programming language pairs, as well as a novel replaced token detection task to improve pre-training with a similar framework as generative adversarial networks. CodeBERT is then fine-tuned for applications such as natural language code search and generating code documentation. I'm really excited about the potential of this kind of technology, especially to help beginners learning how to code with their natural language questions about their code. This video will explain the details behind the CodeBERT model. This video will explain the CodeBERT model, using the BERT transformer architecture to bridge information between natural language and programming language pairs, such as the natural language documentation of this programming language Python function. This is useful for downstream applications like natural language code search and automatically generating code documentation. Semantic code search has become more popular lately with the release of the Code SearchNet Challenge. This takes examples of having a natural language query like how do I center a div with Flexbox, or maybe something like how do I parse a regular expression with JavaScript, and then trying to find the corresponding programming code that corresponds with this natural language query. This is a really interesting application for helping programmers with these frustrating problems that you just can't seem to find an answer to on the internet. I also think that this is a really interesting kind of idea in the zero-shot setting, where you have these kind of like experimental libraries and then you run into problems with them, and then there's really nothing to find on the internet to help you solve your problems. So I think it's really interesting to see these tools for bridging the natural language programming language questions that people have, especially when you're first learning how to program, to facilitate this kind of a learning with these natural language queries. Before we get into the specific details of CodeBERT, we'll do a quick background on the original BERT model. So BERT is kind of like an encoder-only transformer, similar to how GPT-2 is a decoder-only transformer, and the original attention is all you need transformer developed for neural machine translation has the encoder-decoder architecture. So the idea is that you have a masked sentence, two masked sentences that you're masking out intermediate tokens and you're predicting the masked intermediate tokens, and in this way it attends over this entire input sequence as it learns to predict the masked tokens. So say token 8 will be replaced with this mask token, and then the output is predicting that mask token. Another detail about this is the input format. So you have the CLS token denoting the start of this, which is also indexed at the end of the BERT model for the respective task. In this case, they pre-train it with the next sentence prediction, where the CLS token is predicting whether sentence B comes after sentence A, and then in other cases like, maybe not question answering, but say natural language inference, the CLS token would be like entailment, contradiction, neutral, something like that would come out of this spot of the output. You also have this special separator token denoting the difference between sentence A and sentence B. And in the case of CodeBERT, it's going to separate between the natural language sequence and then the programming language sequence. BERT is really easily extendable into multiple modalities. In deep learning, this term bimodal generally describes having two different types of data. So say you have language and vision, or audio and vision, something like that is generally described as a bimodal data set in the deep learning literature. So some examples of BERT combining modalities is particularly with image language with things like ImageBERT or VilBERT, or combining video and language like VideoBERT. So in this case, CodeBERT is going to be combining the bimodalities of natural language and programming language pairs. So you see in the case of ImageBERT, how they take these vision tokens from the object detection network and use this as the visual sequence and combine it with the natural language sequence. And the attention will look at this whole sequence. So this idea of self-attention is looking at this entire sequence to integrate all the information from the sequence in order to perform the respective tasks at the output layer. This video shows an example of one of these natural language programming language pairs. You see how we have this function parse memory, and in the middle of it we have this natural language description, parse a memory string in the format supported by Java, blah, blah, blah. And the idea here is that we want to leverage these natural language descriptions of the code in order to facilitate downstream applications like natural language code search. So later on, if we put a query in like how do you parse a memory string supported by Java and Python, we'd want this kind of function to be returned. So this is the idea of a natural language programming language pair. We're going to format this as sentence A that goes into the BERT model, and then we're going to format the programming language as the sentence B that goes into the BERT model. CodeBERT is trained with two pre-training objectives. These pre-training objectives describe these self-supervised learning tasks that let these models take advantage of these kind of unlabeled data sets that are massive and help it do this pre-training of representations useful for downstream task transfer. So first we're going to go from this raw data set of these natural language programming language pairs, and then we're going to fine-tune the BERT representations on the natural language code search problem. So the idea behind masked language modeling is you have this natural language input and the programming language input, and you're going to randomly mask out tokens and then predict the tokens that were masked out. So you're doing the attention over the natural language and the programming languages in order to inform decisions about the output layer on, so say you use something like, I don't know, the units in this programming language in order to inform a masked token in the natural language part of the sequence, and vice versa. In this paper, CodeBERT, the authors also introduce a novel pre-training objective, replace token detection, for pre-training their CodeBERT model on this massive, almost like unlabeled style text dataset containing these natural language programming language pairs. So the idea behind replace token detection is you have the original natural language sequence and the original programming language sequence, and you're going to randomly mask out the tokens, but then you're going to train a generator model. So it's not quite like a transformer generator model like GPT-2, rather it's just like an n-gram kind of probabilistic, I see this context window, so I assign a high probability to this token. So it's a simpler generator model than these bigger transformers like GPT-2 or what have you. So you take the generated token that comes out of the generator, and then you have this new sequence where the masked tokens have been replaced by the prediction from the generator network. So now this original BERT model is getting this sequence of tokens, and in the output layer is predicting which was the original one and which one was replaced. But differently from, say, generative adversarial network training, if the generator actually does predict the right token, it's going to be labeled as original rather than replaced. Putting this together, the CodeBERT model has 125 million parameters and is a 12-layer transformer encoder similar to the BERT model. An interesting detail about this is that it takes them 250 hours of training on the NVIDIA DGX2 workstation using the 16-bit floating point mixed precision kind of training. So they have these 16 interconnected NVIDIA Tesla V100 GPUs, each with 32 gigabytes of memory, and it still takes 250 hours in order to pre-train this model on the mass language modeling task and the replace detection, token detection task. It's also interesting to see the statistics of the dataset used for doing these two pre-training objectives to get the initial kind of context predictions for the CodeBERT model. You see how you have these distributions between the bimodal data, which is cases where you have the code and then it has the natural language documentation kind of in the code, and the unimodal code, which is unimodal meaning just programming language. So there's no natural language corresponding to the programming language in the data set. You see how you have these differences, particularly in the JavaScript training data set. You see a big difference between unimodal codes and bimodal data, although most of the cases it's pretty balanced, about like 2 times or 3 times as much unimodal as bimodal data, which is interesting because the unimodal data is useful for pre-training those generators in the replace token detection task, but overall it's not that useful in the mass language modeling task, because you want to have the programming language and the natural language together so that you can attend over the entire sequence and learn this kind of a joint representation. The first application they test CodeBERT on is natural language code retrieval. And the idea here is to have a high similarity between the query and the code that matches it. So the idea is that you take the question or the query, such as how do I center a div with Flexbox, or how do I open a file with JavaScript, and then you have the corresponding code pairs that you're looking to match the similarity. So the way that this works is you have the question and then you have the given code sequence, and you're going to index the CLS token in the output to score the similarity between the query and the code, and then you're going to rank the most similar codes to the query as the output to this problem. It's also interesting to look at the data set. You see you have a lot of training samples for PHP, Python, and then not as much for, say, Ruby. So it's interesting to see this kind of data set from the CodeSearchNet challenge. This table shows the results of natural language code retrieval with the CodeBERT model and other baseline models like the bidirectional RNN or the RoBERT model only. So one interesting detail of this experiment is that they find when they initialize the CodeBERT model with the RoBERT parameters, RoBERT is like a slight modification to the BERT model. Basically, in the paper RoBERT, they look at a lot of little details in the BERT training that actually add up and provide a pretty significant boost compared to the original BERT model. But when they initialize CodeBERT with RoBERT, so it has these initial parameters of the RoBERT model that's trained on probably something like web text or one of these kinds of data sets, I'm not exactly sure, but they use the pre-trained representations from the RoBERT model into the CodeBERT. So it's definitely interesting to think of how you transfer from unimodal natural language models like the data set that RoBERT was trained on into something like natural language programming language pairs for the CodeBERT model. It's also analogous to something like how you might do like multilingual BERT, where sentence A is like English and then sentence B is French, if you want to do that kind of thing with the BERT model. So you see in the case of using the mass language modeling and replace token detection to further pre-train the model after being initialized with the RoBERT parameters, you get a much higher performance than when it's initialized from scratch and then you're pre-training with the code only or when you're doing the original case where you only do mass language modeling and you have a random initialization. In order to get further insight into how the CodeBERT model makes predictions and how it differs from the original Roberta model trained on natural language only, they do this kind of zero-shot natural language programming language probing. So zero-shot describes how they're doing this in the validation and test set, meaning that the CodeBERT model hasn't already seen this data, and that's how they're describing zero-shot transfer into this domain. So the idea behind their natural language programming language probing task is that they're going to deliberately mask out these tokens that have either min, max, mean, these kind of tokens that from the natural language perspective are pretty similar to each other, but in the coding language particularly setting, they're very different kind of ideas. So you see the difference between the probability distributions on the first token between the Roberta model and the CodeBERT model, and then you see an even more dramatic difference in the programming language part of this kind of a sequence to tell just how fine-tuning the model on the programming language pairs gives it more insight into programming languages compared to a model like Roberta only trained on natural language. The authors then test CodeBERT on code documentation generation, attaching a new decoder part to the BERT-only encoder in order to produce these generations. So you see the performance achieved by doing this CodeBERT compared to just having a transformer or a Roberta or a sequence-to-sequence model that encodes the programming language into the input to this decoder that is now randomly initialized. So all these models are encoders, and then you're attaching it to a new decoder in order to test this documentation generation task, and it's evaluated with this blue score between some kind of baseline of maybe like a set of human written documentations for the code. Another interesting experiment they perform in the study, although it doesn't quite outperform this code to sequence model using an abstract syntax tree, is zero-shot documentation generation to C#. So what's interesting is that the CodeBERT model has never seen C# code before, but now it's in the setting where it's given some C# code and it's going to try to describe it in natural language with this appended decoder part to the original CodeBERT encoder model of the C# code. So I definitely think it's interesting to think of this zero-shot documentation generation and look at the results achieved by the CodeBERT model. Thanks for watching this explanation of CodeBERT, a really interesting adaptation to the BERT model to bridge information between natural language and programming language pairs. I think that applications of this kind of natural language code search will be really useful for people who are just learning how to program, as well as people who are dealing with this almost zero-shot setting where people are constantly releasing these new libraries and frameworks, like a new release to PyTorch, a new environment like Torch Meta, or some new benchmark like the Fire environment or something like that, and you're trying to figure out how to debug these problems. But it can be difficult because there's not that many people on the internet on, say, Stack Overflow writing about these GitHub like issue logs that are writing about these problems. So to have these kind of models that can bridge the natural language programming language gap automatically could be so useful for these kind of head-scratching programming problems that you come across. Thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.